So we've looked at a couple of contexts in which we have a natural notion of high order, if you will, high level specifications giving rise to algorithms which preserve symmetries. Question really arose in the context of relational databases, and it was in that context that Chandra and Harold asked the question whether one could formulate a relational database query language which defined exactly the polynomial time decidable properties. It turns out that question has a natural formulation in logic, and that's the context in which it has been much studied. Now, I want to look at another context of work in complexity theory, that of circuits, where a natural notion of symmetry arises, and it sort of makes concrete the idea of what it means for an algorithm that we compile down to being symmetric. So I'll give a very brief introduction to circuits. More details will follow later. A language, in other words, a decision problem, let's say over strings of symbols, zeros and ones, we can think of it as a family of Boolean functions. So fix the length of a string n, and we then have a fixed finite Boolean function which takes strings of zeros and ones of length n to zeros and ones. And any fixed Boolean function can be computed by a circuit using just, let's say, and, or, and not gates, or maybe further gates like majority gates. So we think of, in other words, this Boolean function fn is computed by a circuit. The inputs to the circuit are n Boolean variables x1 to xn, so each one of those can take a value 0 or 1. And once you give those values, we can compute this, and we have a single output gate which gives us the result, which is again either 0 or 1. Okay, and we think of this as saying being 1 if the string on the input is in the language L, and 0 if it's not. So any language whatsoever, decidable or not, can be expressed by a family of such circuits. In the case where we have an algorithm for deciding the language, we can think of the circuit as being obtained by fixing the length of the input and unfolding the behavior of the algorithm to eliminate all loops and just make it a sort of straight line algorithm. If the size of the circuit is bounded by a polynomial in n, then the language L is in the class P/poly. Again, there's no assumption of decidability here. You can have undecidable languages in P/poly. It's just the size of the circuit is bounded. To get indecidability, we can put in the additional condition that the function which, given n, produces the circuit is itself computable in polynomial time. And then this is a characterization of P. So P is the class of those languages for which there's a polynomial time computable function which, given n, will give a circuit of size Cn, whose size itself is bounded by a polynomial in n, which is necessarily the case if this is computable in polynomial time, such that this family of circuits decides exactly this language L. Now, when we consider the classes of languages P/poly and P, it makes no difference whether we just consider and, or, and not gates, or we add a richer basis with threshold gates or majority gates. And that's the reason is that each of these gates can itself be computed by a circuit of polynomial size, so we can just replace them by circuits which compute them. Now, part of the interest in circuits is that people think of this as a way of establishing lower bounds, of proving, for example, that P is different from NP, or even the stronger conjecture that NP is not even included in P/poly. So what this conjecture means really is that when you take an NP complete problem, not only is it not computable in polynomial time, but in some sense there's a fundamental combinatorial reason for it, in that consider the following model of computation. I tell you the size of the input, and then I allow you to do anything you want. You can take any amount of time you want. In fact, you can do uncomputable things, whatever you want, based on the size of the input. And at that point, you can say, right, I'm ready for the input. And then I give you the input. But from this point onwards, you're only allowed a polynomial number of steps. That's really what P/Poly is about. And what this is saying is that NP-complete problems can't be computed even like this. That is, for any particular input that you really need to do a super polynomial amount of work. That's what this conjecture is saying. In pursuit of this conjecture, of course we don't know how to prove it, but in pursuit of this conjecture, people looked at further restrictions on the circuits and prove real lower bounds. One of the classic examples is the result first proved by Sachs-Sipser, and independently by Ita, I should say, which says that if you bound the depth by a constant, then no polynomial size family of circuits decides parity. Parity meaning just deciding whether the number of ones in the input is even. Rousborough showed that if you restrict yourself to monotone circuits, then you can't decide problems like clique. No polynomial size family of monotone circuits decides clique. Rossmann gives a sort of bound for constant depth families of circuits deciding clique by showing that you cannot get such a family of circuits whose size is n to the k over 4 if you're deciding k clique. Okay, so this is so these lower bounds are obtained by either bounding the depth of the circuit to constant or putting a restriction of monotonicity, which really means you don't have any negation gates. But if you allow majority gates in addition to and or and not, okay, I said before that this makes no difference to P/Poly. But if you're restricting yourself to constant depth, it does make a difference whether or not you have majority gates, because implementing majority gates with and ors and not requires possibly, we think, more than constant depth. So throw in majority gates to constant depth polynomial size families of circuits, and we have no separation of NP from this. Now, we are looking, so circuits is again a very low-level model of computation working on bit strings. We're thinking of the situation where we formulate an algorithm by a high-level specification on an abstract data structure such as a graph, and then we compile it down to a circuit. Okay, so the circuit is deciding properties of, for example, graphs, right, or other relational structures. Let's just think about graphs for the moment. A graph on n vertices, let's say a directed graph, has n squared potential edges, right? So there are n squared pairs of vertices, each of which may be an edge or not. So in other words, for each potential edge, there's a value 0 or 1. And so this sequence of n squared zeros or ones describes the graph. Okay, this is very much like our string encoding of relational structures, just except we're restricting to one binary relation. We provide that binary relation as an input to a circuit, and the circuit tells us whether the yes or no, and it decides a graph property. Okay, so graph properties in P are given by such families where the size of the circuit is bounded by a polynomial in n, and the family is uniform. So again, the function which goes from n to Cn is computable in polynomial time, or you can make it more restrictive, for example, d log time. Now, not every such family of circuits decides a graph property for the reason we've alluded to before, namely, you can have more than one string encoding the same graph, and the circuit might give us different results. Okay, so we say the circuit is invariant if this doesn't happen. That is, if you permute the inputs by a permutation of n, then the result is unchanged. So in other words, think of the graph, as we're doing, as a function which takes the n squared potential edges, and for each one gives a value of 0, 1. This edge is either absent or present. Then if you take a permutation pi of the elements 1 through n, then the circuit which accepts the graph should also accept the string, the n squared long string of zeros and ones obtained by applying this permutation to G, right? So you look at the graph that I call pi G, whose value at ij is what G does on pi I, pi j, right? This is what we call an invariant circuit. And any invariant circuit then defines a graph property. This is not the same as saying that the circuit is invariant under all permutations of the input. A circuit like that would only allow us to define functions of the number of ones in the input. But this is just saying that the circuit decides a property of graphs. Really, it is saying we introduced this tilde equivalence relation on strings encoding relational structures. Think of this just restricted, as it were, to one single binary relation. So we have a string of zeros and ones representing a binary relation, and two strings are equivalent if one is obtained from the other by such a permutation. And we want that the circuit does not distinguish two equivalent strings. So we say that a circuit is symmetric if whenever you permute the inputs in this way, you can extend that permutation to an automorphism of the circuit. In other words, the shape of the circuit, you can permute the gates in the circuit so that it looks just the same. Okay? Formally speaking, for each permutation of Sn, there is an automorphism of the circuit which takes the input, which is labeled by the pair ij, to pi I, pi j. Right? You apply the permutation pi to both components of this pair. If you have a symmetric circuit, then it is necessarily invariant. That kind of you're just imposing this by the structure of the circuit. But the converse is not true. Consider the natural circuit for deciding whether the number of edges in an n-vertex graph is even. Let me draw this. So, say we want to decide whether the number of edges in an n-vertex graph is even. Okay. Here's how one way of doing it. Take the XOR of the first two. XOR that with the third. And so on. Okay. Now you can, I'm using XOR here, but you can always implement XOR using just ANDs and ORs. You can make this more efficient, make it logarithmic depth instead of linear depth by, making this as closer to a complete binary. There's various ways of optimizing it, but this is not symmetric, right? In the sense that, for instance, if this is the edge 1, 2, and this is the edge, the potential edge 2, 3, then swapping 1 and 2 should, or maybe let's say swap 1 and 4, should take 1, 2 to 4, 2, but it leaves 2, 3 unchanged, right? So that permutation will take this first gate to the gate labeled 4, 2, which may be somewhere here, but it leaves the second gate unchanged. So this one should map to something which connects 1, 2, and 4, 2, which connects 2, 3, and 4, 2, but there isn't such a gate. Okay, so this thing is not symmetric. And it turns out that with just AND, OR, and NOT gates, you cannot get a symmetric circuit for computing the parity. But with, I should say you can't get a symmetric polynomial size circuit for computing the parity of the number of edges. But if you add majority gates, you can. Okay, but that's something we will come back to later. Okay, so you can always convert an invariant circuit to a symmetric one, but with a potentially exponential blow-up. I want to refer to a connection with logic. So remember, logic is our kind of canonical language for giving high-level specifications of what, say, graph properties. And we can automatically translate a formula into a circuit family. And let's look at this for first-order logic. So what I would do is, given a formula phi, a sentence phi, let's say, take each formula with free variables x and consider all possible, okay, so I should say, I've fixed the formula and I've fixed the size of the input, n. So I'm interpreting this formula phi in structures with n elements. Consider each assignment of values to the free variable. So I may as well assume that the elements of my structure are 1 up to n. That's the set. Okay. And if I have k free variables here, there are n to the k different ways I can assign values to the variables. For each one of those, I create a gate in the circuit. Existential quantifiers translate to big disjunctions, etc. What does this mean? So if you have a formula, there exists x. Let's call this theta. Then for each value of x, you will have a gate in your circuit which evaluates theta at that value of x. You'll take a big disjunction of all of these, right? And if psi is your formula, then this is your formula psi. Now, psi may have additional free variables. And of course, in theta, you have all those free variables in addition to the free variable x, which you've assigned this value. Okay. So the circuit you obtain has constant depth. It's given just by the depth of the formula, right? Because really each quantifier adds one more layer to the circuit. Its size is some constant times n to the k, where n is the size of the structure we fixed, and k is the maximum number of free variables in any subformula of phi, right? Because for every such formula, we create n to the k different gates, and c is the number of subformulas of phi. Moreover, the circuit we get is symmetric in the sense we defined, in the sense that if you take any permutation on the set 1 through n and apply it to an input, you can extend it to an automorphism of the whole circuit by taking the gate psi a to the gate psi pi a, right? So all that this means is apply the permutation pi individually to each of the elements in the tuple A. And this is a well-defined gate. And it's not too hard to see that this defines an automorphism of the circuit. Okay, the circuit we've just constructed. So what do we conclude? We conclude that formulas of first-order logic have an automatic translation, once you fix the size of the structure, to circuits of constant depth, polynomial size, and which are symmetric. As a last example of symmetry arising naturally in theoretical computer science, I want to talk about linear programs briefly. So back in the 1980s, there was a great deal of excitement at the discovery that linear programming could be done in polynomial time. It was linear programming is so pervasive in solving combinatorial optimization problems. Some people thought that maybe the discovery that there are polynomial time algorithms for it could lead to polynomial time algorithms for hard optimization problems, such as NP-complete problems. So proposals were put forward for encoding hard problems, such as the traveling salesman problem, as linear programs. And I will say a little bit about this later on. And Yannakakis proved that any encodings of the traveling salesman problem as a linear program satisfying certain natural symmetry conditions must have exponential size. Now, It's not the case that any encoding of the traveling salesman problem as a linear program must have exponential size, because if you could do that, then you would separate P from NP. There were symmetry conditions. And because I'm short of time, I'm not going to explicitly go into what these symmetry conditions are. We'll do this in more detail in lecture 4. But I just wanted to point out this was an entirely independently arising notion of symmetry in the encoding of problems, which turns out to have a relationship to the other notions of symmetry we're considering. And the reason for considering it, the reason put forward by Yannakakis, was that any natural way of encoding a problem like the traveling salesman problem into a linear program seems to have symmetries, because if it's natural, it kind of encodes the symmetries of, it reflects, I should say, the symmetries of the problem itself in the linear program. Okay. Relation of the symmetry condition and what the lower bound actually means is something we'll explore later. But for now, we're out of time, so I'm going to stop this, and this is the end of lecture 1. Thank you.